My name is Michael Wong. Among other things, I'm the concurrency technical specification editor as well as chair of SG14 and SG5. This is not just any talk about parallel STL. There's been a number of them, and they're good ones, teaching you how it is possible to run the standard template library algorithms in parallel. We're going to show you how it's done not just on the CPU as is specified in the standard specifications in C++17 right now, but show you a vision of the future where it can be done on GPUs. And indeed, we've done it. We've actually implemented so that it can be executed on the GPUs itself. This is where the power of the specification really comes in. We're going to show you a demo of how that works and also give you some directions about where the future direction is. So, a lot of these talks are going to be beneficial because we gain experience and benefits from a lot of people's help. And this is no different. We shared committees on C++ as well as Kronos. Kronos holds some of the specifications that are dealing specifically with heterogeneous computing. And indeed, both committees are going to benefit from sharing knowledge in both directions. But there are going to be necessary things mistakes that are remaining, and I claim all of them for myself. I like to claim all the good stuff for myself, but in honesty, I just can't allow myself to do that. The usual legal disclaimers, I'll go over that. Our company is CodePlay. We work on heterogeneous computing tools. This is why we've gained so much experience, and we've been participating in both standards for quite some time. We have products that generally allow you to distribute to any OpenCL devices, but using very modern C++. All right, so in this talk, we're going to give you a bit of the history and the background of STL, or Parallel STL, because we have been there since the beginning, being involved in driving some of the directions. It actually started with a question back in, I forget which meeting I was at, but it was just after C++11, and I raised the question, when can we get the C++ standard library to be working in parallel? And from that point on, it galvanized. I'm not saying I'm the only one. There were a number of other people as well too. It galvanized a number of collaborations. Because we've been following it so closely, because it affects us so much, especially at CodePlay. We have been looking at this is actually an excellent example of what it takes for a technical specification to reach C++ standard ratification. You see all the changes. Now, up till now, people have been saying, well, technical specification, on the one hand, some people might be saying it's 99% there. On the other hand, some people are saying, well, it's just implemented and there's a lot of changes. And by the time you get to a standard, it might be very different. The reality, actually, as you will see, is somewhere in between. We're going to show you how Parallel STL works on CPU. Very briefly, you've probably seen 100 other, well, maybe not 100, but quite a few other talks already about that. The concept is remarkably simple, so it really doesn't take a huge number of slides. And then of course we have one more thing. We're going to show you how it works on a GPU, what it means. And again, it's actually remarkably simple. The implementation isn't simple. One of our engineers who's implemented it here under the team that we have at CodePlay is going to show a live demo. And then we're going to do one more thing again, and that is I've been leading this group called SG14, which has been driving for heterogeneous C++ and distributed C++. And I'm going to show you where we're going with all the different proposals that we're going to foresee in that future direction. All right. So, just a few things about Parallel STL. I've already mentioned that there was a wish that by the group after C++11 came about, and recall C++11 gave us a fairly simple basic thread interface, multi-threading, with atomics and with an atomic and a memory model, but nothing else about the library capability towards parallelism. And there had already, excuse me, there had already been directions in that outside of the committee. For instance, GCC had a parallel STL implemented using OpenMP. There was another effort at Texas A&M University called Staple, okay? In Beyond Strauss's group. So people have tried that, and they've already noticed certain things you could do in parallel and certain things you can't do. You can't do push and pop over and over again because that's fundamentally sequential. So there were but there were certain other algorithms that didn't involve push and pop a great deal that you could do in parallel fairly quickly and easily. Accumulate was in fact one of the top on the list. Okay, so it seems reasonable to look at the industry and gather some of that experience. Now, in today's current desktop technology, you see that there is a combination of explosions between the number of cores and the GPUs that's either attached in a discrete manner, or in some of these cases, with Intel, the GPU core is more or less combined with the CPU cores. There are other directions right now towards more massive parallelism, where you have millions, essentially millions of GPU cores, depending on whether you're doing things like high performance computing or distributed computing. If you're doing distributed computing, you might indeed be attaching multiple nodes here. Okay, and in that direction, Hartmut Kaiser had a great talk talking about how you can use HPX to essentially do initially distributed computing, and subsequently he added heterogeneous computing capability on top of that as well too. And we have always headed towards a heterogeneous direction. And whatever we took from C++, we would always try to see, okay, how do we do this using heterogeneous computing? How to send it to multiple GPU cores? We've been hired by various companies to do that, especially when they're doing embedded processors that are embedded GPU cores. So from a software point of view, various companies have already put software on the table back in as early as 2012, just after, even before standard ratification, that can allow you to run the library on the GPU. So we're talking about two things here. One was to do it in parallel, okay? The other one, and I talked about it with the GCC libraries that was using an underlying OpenMP layer. Beyond that is also doing it on the GPUs, okay? And doing it on the GPUs, there was demonstrations of that using NVIDIA's research divisions called Thrust. AMD had a similar one called Bolt. Okay, Microsoft and Intel, of course, had the Intel TBB, thread building block. And of course, there was Parallel Pattern Library and C++M. So the world had a large number of mixtures of experience in this, but they were non-uniform. Some were really only working on CPUs. Some were working in parallel, and some were working on GPUs only. Okay, so things like Thrust and Bolt were mostly for the GPUs, okay, whereas the other ones were mostly for the CPUs. But nevertheless, they were all trying to do it in parallel. So the committee, being mostly conservative, started trying to do it, and because the C++ standard really still doesn't admit anything about any other separate memory, other than the CPU memory in a flat memory, essentially a flat memory layout. All of what we did was essentially the proposal centered on having it run in parallel on just CPUs. So the first proposal appeared in 2013 under a parallel algorithm library, and essentially combined the experience from TBB, PPL, Thrust, to just essentially abstract out what it meant to run this algorithm on the CPU only. And over time, there was a lot of iterations until it culminated in Jacksonville in 2016, I believe. Yes, it says that. I'm just going from memory. Now that looks interesting there. You see the long timeline in between. There were a lot of obviously something like this going into the standard. You might think it's simple, given that there's a lot of prior art and prior experience. But trying to fit it into the standard resulted in a number of interesting changes. And indeed, there were actually many clarifications and corrections, even after this point before it reached 2017. And indeed, most of these are much more noticeable because they were decisions about changes to a TS that already has been published. So the result, I would say, is it's not true that you can't change things after a TS. And indeed, the learnings from the TS is extremely valuable. This is the message, the takeaway that I got from it. That TS is an extremely valuable instrument, especially and only if you have implementations already using it, trying it out, and demonstrating and giving feedbacks to the committee. And indeed, there were, let me see, do we have that slide? That slide about the number of implementations is later on, but there were actually about 5 or 6 implementations. Some had already implemented from before, some implemented after, like we did at CodePlay. So the number of changes were actually quite a large number. This is actually a summary, mostly for my recollection of all the changes. I'm going to go over each one of them because they're kind of interesting. Once we got it in the TS form, the first thing we looked at was this idea of a dynamic execution policy. This is the idea where the execution policy, which is the PAR, whether you say whether the parallel algorithm is to be executed in a parallel or sequential or parallel or vectorized manner, you could substitute that with a variable name that you can change dynamically in flight during program execution. We changed that because we felt that this would effectively change the state of the algorithm. And we didn't want that to happen yet. We might want that, but we had concerns about that as a committee. So that was the first thing that was dropped. The second thing that we changed was the name. For a long time there, we wanted to look at, we had 3 names. One which was seq for sequenced, meaning that it's running in a sequential manner. The second one was par, meaning that it's running in a parallel manner. The third one was par_vec, meaning it's running in a parallel vectorized manner. So for a long time there, we looked carefully at that third name, par_vec. While it conveyed the name relatively clearly that you want to run it parallel and vectorized, there was concerns that this is not always going to be true. Because the ability to run these is relatively optional, especially at a higher and higher parallel manner. Some hardware might not actually have the capability to support vectorized capabilities. In such cases, the algorithm is actually allowed to drop you back to parallel, and if parallel was unsustainable, it could actually drop you back to sequential. Okay. Now, the friendliness of your implementation might actually inform you of that, but it all depends. So at that point, we decided to change the name to unseq for parallel and vectorized. And that was a good change because it really is saying that this is parallel, but the predicate functor that is the deciding quality of your algorithm is going to run in an unsequenced manner interleaved on multiple threads. So it was more descriptive, whereas the name vectorized could mean different things to different implementations. The next thing that happened was a flurry of changes. So those first 2 changes actually happened fairly far apart. Then starting in mid-2016 in Oulu, Finland, a number of changes started coming much more rapidly because of a more recent implementation experience. And this tells you the value of something like this. The next 2 changes came because someone really looked closely at the exception policy of these guys. And the exception policy, the way it worked was that we would, for every exception, we would generate an exception list, and the exception list essentially is a vector. Hanging off the vector would be these exception pointers. Now, this, in theory, sounds great, like most designs, but when it met the metal, imagine you actually had a parallel algorithm running, and hundreds of exceptions starts pouring out. This vector would grow almost uncontrollably. That's the key problem there, this growing of this vector. Now, vectors can grow, and that's very nice, but, well, if it's growing dynamically while the program is running, can you imagine what that would be like in an actual operating environment? Yes, you can. So, we killed it. We said, that's just unsustainable. No one else actually implemented it except one company. CodePlay actually implemented it. Okay? We did, right? And we also thought it was weird that this was decided. So certainly this was an important thing. Key among this was Bryce Laubach, who actually was working at Berkeley at the time, and he certainly came back with the opinion that during his implementation attempts or looking at it, he felt that it was unimplementable. So we definitely killed it. We made it so that if any exceptions came out, it would just terminate and unwind. Now, before you think that's a bad idea, in parallel, please note that C++ has no policy right now to handle exception in a concurrent environment. We have exceptions in a sequential environment, but we have no idea how to handle it in a concurrent environment. Neither does the rest of the world. And in such an environment, we have to essentially pull back and say and use the most coarse-grained method available to us, and that is just to terminate. Now, I can draw that parallel experience with other standards. In OpenMP, for instance, if you have an exception that escapes a parallel region, that's all they would do as well too. In many other parallel models, this is exactly all they do because they can't think of doing anything better. The world actually do need a better exception model in a parallel environment, and we're working on that. The next thing was that we noticed that along as a drive-by shooting, we thought, okay, now that we changed that, what do we going to replace it with? This exception policy. Well, we don't know. We don't have enough time. We're going to go to standard ratification in a couple of months. In fact, the cutoff had already happened in the last meeting in the Jacksonville meeting. This is after Jacksonville. So you don't have time to redesign things now at this point. What do? Well, we can't let exceptions sit where they are right now, which is that they were attached to the algorithm. That meant that if we try to replace it, we would have to replace it for every algorithm. That's just not a tenable proposition. So we thought that at that point, let's replace it with let's move it so that it's now attached to the execution policy. Okay? At the execution policy are these names like sequence, seek, par, and par unseek. That's the name that's been changed. So by attaching to the execution policy, now it gives you the flexibility in hindsight of being able to change this execution policy as we invent a new one. Okay, sorry, to change the exception policy as we invent a new one. From that point on, the changes come even more rapidly. Bryce in particular noticed that there were incongruent names involved with the numeric aspects of many the numeric aspects of STL that was under the Parallel STL name, mostly names like transform, reduce. So most of that was changed under the next two papers. The next, and then at that point, Parallel STL was mostly incorporated into the draft C++ 17 specification. And so this was basically about late last year, and C++ 17 went to ballot for international voting. At that point, a whole new flurry of comments come in, and that include the bottom two. Principally, Switzerland came in with 2 comments, which was extremely interesting. And this demonstrates how it works as an international standard. Switzerland noted that some implementers, namely would co-play SYCL, which is essentially a modern C++ on top of that allows you to distribute to heterogeneous environments immediately. We would actually have to copy the argument into another place, okay? Because it's a heterogeneous environment. The argument might come through from the CPU. It would need to be copied into a neutral place so that it could potentially be moved to the GPU for execution. You'll see that, okay? We don't copy everything over. We only copy what's necessary over. So this cloning is actually not allowed by the specification, because they never thought that they had the intention of this happening, because thrust was one of the backgrounds, the NVIDIA thrust, which operated on GPU, but it was meant to work only on a CPU. So they never thought of designing it like that. So one of the comment was that you couldn't make this copy. So we had to argue for quite some time around the committee so that we can enable this cloning of this argument in order to enable SYCL to work properly. Well, in reality, we actually didn't need it. And I'll show you why, because the reason we worked it out, is because we didn't use any of the standard execution policies. What these things did was that it enabled you to do them on standard execution policies, the named ones, like par, unseek, and seek. Okay? We didn't want yet another implementation where you couldn't do things in a standard way, because most of the implementations at that time, like HPX, which implemented it, and SYCL, which implemented it, was actually not implementing on the CPU. That wasn't the point. They were trying to do it on distributed nodes, and The problem also exists on distributed nodes because they also have to clone the arguments to the different nodes that they want to send it to. Just like on heterogeneous computing, we have to clone the arguments to the GPU node. HPX would clone it to the CPU nodes. Okay? So the standard did not allow that, so we had to fix that area. There were other additional fixes that went on that actually had to be done. There was the idea that you couldn't invalidate these because it's a vector. Vectors normally cannot be invalidated and kept in the same shape. Okay, so this changed I want power saving. Maybe this is on power saving mode. I hope this comes back. Yeah, I'll keep talking. So what it did was essentially it had to change the idea that you had to do, instead of forward iterators, so we had to switch between forward iterators and random access iterators. So in combination, all these changes enabled the final version that got into the C++ 17 standard. So as you can see, what got into the C++ 17 standard is non-trivially different, okay, than what's in the TS. Although most people might miss all these little details, I was painfully aware of every one of them because I found it was necessary to drive this so that it was an enabler for future directions for distributed and heterogeneous computing. Thank you for reviving this. Next part. All right. I don't know why it's blank, but that's sometimes happen. So let's so after all that, let's take a look at what it means. I probably should have done this at the beginning so you have some concept of what I was saying, but it's essentially, the whole idea is relatively simple. You have all these these STL algorithms, and if you say nothing at the beginning, like up here with sort, if you say nothing, it's assumed the same as before. It's going to run in a sequential manner. If you put the word a standard execution policy of seek in there, that's the same as if you said nothing. Okay, it will still run in a sequential manner. If you add the par execution policy, it will now run the predicate in a parallel manner. Okay? And these execution policy creates a new namespace that is called the sequential, the parallel, and the parallel unsequenced. As I said, parallel unsequenced name was changed. So sequence is just do it normally as in C++ 11. Parallel adds the ability that the caller may span to other threads, and the invocations, but on a single thread, the invocations do not interleave. Whereas with parallel unsequenced, it relaxes it yet again so that the invocations of the predicate is going to be interleaved on a single thread. Now, as I said, these fall back on each other. If the hardware is not capable of implementing it, it just keeps going down so that it's always going to be executable. Now, this actually opens the door for many other execution policies, and indeed, several others are now being talked about in the next the Parallelism TS2 with the idea of SIMD executions. When you're doing SIMD execution, which still right now only talks about the CPU, but we were always keeping in mind that it has to work also on the GPU, because that's all GPUs is about SIMD execution. We have invented additionally, excuse me, additional policies that's going to go on top of these three that is going to help us manage SIMD executions. So I mentioned that there were a large number of implementations, and indeed most of them have been ongoing between Microsoft, HPX, HSA, Depot, NVIDIA, and CodePlay. We think that there's still no Clang implementations. We welcome if we're proven wrong. Using the execution policies is extremely simple. Okay, you just have to add this additional parameter at the beginning. What's interesting is that there is a custom vendor policy, and this is the escape door, backdoor that most of us at HPX and SYCL use, because we created our own vendor execution policy, which allow cloning, all the special kinds of iterators that wouldn't invalidate, so that we actually can make it work properly in that special environment. Propagating the execution policy to the end user is quite simple, using a library or template here. Okay. And not all the not all of the parallel algorithms, libraries were implementable, of course. Only a few were not implementable in a parallel manner. So as a result, almost all of them were. I don't think we have a list of what was not, but that's not hard to find, I suspect. But there's a couple of new ones that we added, such as for each and for each n. Some of these are fairly easy to be re-implemented using, for instance, OpenMP. For instance, some of these could be just implemented, especially if the execution policy is POVEC, with an OpenMP parallel region for using a SIMD. And that's probably all you have to do, and attach a following for loop to it, and that would all that you would need. You could also do this very easily in OpenCL as well too, or whatever favorite private language you have, whether it's CUDA or whatever it is, or HSA that you wanted to implement. So this is why there's so much industry experience in this. What this does differently is that it elevates all those many different implementation styles into a higher abstraction, so that you just have one high abstraction that can do it, and then it doesn't matter what your underlying policy is, you assume that they're going to optimize it for the best underlying hardware. And this is exactly the point of C++. And the point of what I had been talking about yesterday in one of my talks about parallel programming, and that's to elevate the generality of your design such that you can increase productivity. Now you're no longer focused onto the underlying details of which GPU or which CPU I'm executing this for. There are other additional new algorithms like reduce, as well as, and these guys give you the ability to do things that are very interesting parallel programming patterns. I'm working on a different talk that deals with this, but this is essentially a serial reduction algorithm, because we're doing this with no extra parameter, as you can see. So as a result, it's run in sequential. But very easily, you can think of which is very commonplace now in the parallel programming world, where you have a parallel reduction pattern that essentially do things cooperatively between multiple variables that you can now reduce down to one. Okay. Every language that I've been in, parallel language I've been involved with between OpenMP, OpenCL has a specific name for these ones. Usually they're just reduced. So it's time to create a standard one. There are also transform algorithms, which is essentially a map, and that's essentially the idea. You map it to something else through a particular through a specific function that you would give, that you would operate on every single element, and you can do that in parallel. This works only particularly well if it's particularly embarrassingly parallel. If there's dependencies among them, that's basically caveat emptor. And this is what this is saying. You really have to know your data to use these things. Well, you can't just sort of apply it blindly, because the compiler transformation or the library transformation will apply it pretty blindly. Okay. At this point in time, anything of flow dependencies or output dependencies or anti-dependency is all up to you. Okay. There are also additional algorithms that was added for transform reduce. You notice one of the defects that we had tried to address was to set the names for these things. So with transform reduce, it's a fairly good idea in that you also, while you're doing a map, you also do a reduction at the same time. So this is also, as you can see, combines the two previous parallel patterns. So what can I do with a parallel for each? Well, the traditional case is that for each uses only one core. Rest of the die essentially is unutilized. That's too bad, because we do have all this flops lying around. So you could do something like a fill or for each, so that the workload is now distributed across the cores. Okay. One of the things about Amdahl's law and Gustafson's comment about Amdahl's law is that you have to expand the workload as your parallelism increases in order to fully be able to be productive. And so the question, of course, is in this case, what do you do with the GPU part? Okay, that is still right now unutilized. And in other talks that I've given and Sean Parent has given, you notice that most of the gigaflops, in fact, I dare say almost 75% of the gigaflops reside in that area of the die, and it is totally unused. That's a shame. And that's something that we hope that we can correct, and we hope that you guys all can help us in that direction. So the next part I'm going to show you is there's one more thing. It's going to be about how it works on a GPU, and for that my colleague Gordon from CoPlay is going to come up and do a really nice demo that I hope you can see for the first time, parallel algorithm on a GPU. Thank you, Gordon.
Thanks, Michael. Everyone hear me okay? Yep. So, as Michael says, my name is Gordon. I work, I'm a senior software engineer at CodePlay, where I work on CodePlay's implementation of SYCL, as well as contributing to the standard itself. So, I'm going to give you a sort of brief overview of what SYCL is, how it works, and then how we used it to implement ParallelSTL for GPUs. And then I'll give you a little demo of that running. So continuing on from what Michael was saying, if you want to utilize the GPU side of the die as well, what we've done is we've extended the standard execution policies of C++ to use SYCL policies. And these policies allow, through SYCL, execute the work on a GPU or a CPU using OpenCL underneath. So this is an example of the fill-in or the for each using a SYCL policy. And so essentially this is all you need to do. You switch in the standard policy for a SYCL policy, and then the work is then using the SYCL implementation executed on GPU cores. Yep. So we also have, there's an additional policy we also provide called the heterogeneous policy. So this kind of goes a little bit further. Rather than executing your work on a single GPU or a single CPU, it allows you to distribute the work across two GPUs or a GPU and a CPU and work share across the cores. Okay. So these, in the ParallelSTL implementation using SYCL that we have, it's publicly available in the Kronos GitHub. This is the functions, the algorithms that we have implemented at the moment. Okay, so I'll give you a sort of a very brief overview of what SYCL is. So essentially, or traditionally, if you wanted to write code for sort of a open standard way of writing code for a GPU, you would use OpenCL. OpenCL traditionally is a C-based language, so it involved quite a lot of boilerplate code, and it was quite a lot of work to get things running on a GPU or some other heterogeneous device. So what we wanted to create a standard for a single source C++ programming model. So the idea is you write your code for your GPU in standard C++ in the same application, as the same source file as your application code. So we designed SYCL to be based on top of OpenCL, but using standard C++. So this is a kind of overview of what the ecosystem looks like. So generally with SYCL, you would implement your C++ application using template libraries using the SYCL API. So you'd write algorithms and libraries using the SYCL template library. Then when you run this, it uses OpenCL to run your code on a various number of different OpenCL devices. So any OpenCL device can use SYCL. Okay, so I'm going to give a very quick sort of example of what the SYCL interface looks like, using a sort of vector ADA example. So here, the first thing we do is, so we include this. So the first thing we do is, oops, make sure this is working. It's not working very well. So the first thing we do is we include the SYCL header file. So this includes everything that you need in order to write your kernels that run on a GPU. So here we have this function called ParallelAdd. It essentially takes two input vectors and returns an output vector with the result. And the idea is it'll add each element of the two input vectors together and assign it to the output vector. So in SYCL we have this idea of buffers and accessors. So essentially what this allows us to do is, so when you create a buffer, it's essentially maintaining a piece of memory across the host application and one or more devices. So and then we have this idea of accessors, which we'll show in a moment, which allow you to define a particular kind of access to that memory on a certain device. And what it allows SYCL runtimes to do is kind of very efficiently track the dependencies of your application and make the data available when you need it. So the next thing we do is we create a queue. So this is essentially the object that will manage the device that you're running on. So this is what you can queue your work to. Next thing we do is we create this what's called a command group. Command group is essentially it's a C++ function object, so it's a lambda or a function, callable function object that it defines three things. So it'll define the function that you're going to execute. It'll define the accessors, so it defines the memory that you want to access on the device, and it'll define the range of execution, so the different number of iterations of the function you want to execute. So first we define these accessors. So essentially here we just request access to the buffers that we defined. So there's two inputs and one output. And you'll see the two inputs provide read access and the output provides write access. So what this does is allows the runtime to know what you're reading for, what you're writing to. So if you were to read from multiple places at the same time, you could do that concurrently, but if you're writing to something, it'll prevent you from writing to it from somewhere else or reading from it somewhere else because it's being modified. And then finally we define this parallel for function. So this takes a lambda or a function object that defines the actual function that will be run on the GPU. So first thing it takes is a range. So the range essentially specifies the number of elements that you want to execute across. So here we're using the size of the vector. So whatever size of the vector, that's the number of iterations of the function that will be executed. And then we have this lambda function. The lambda function takes a single parameter, specifying an ID. So this ID represents for each iteration, this ID represents the index into the space that you're executing across. And then finally we add the code for the function. So this essentially here we're just using subscript operators on the accessors. So the accessors can be used very much like pointers. And here we're reading in from each element of the two inputs and assigning it to the output. And what happens there is, so another property of the buffers is buffers will synchronize your memory on destruction using RAII. So when this function returns, the buffers are destroyed and the memory automatically waits for the function to finish, and it will synchronize the memory back to the original pointer that you provided it with. So that means that after parallel add returns, the computation is done and the results stored in the output vector. So to jump back to ParallelSTL, so this is a kind of slight overview of what the Parallel STL execution policy looks like. So we provide a couple of different ways of doing it. So the first is if you just create a policy by default, it will pick a device for you. So one of the features of SYCL is it allows the runtime will pick a device, the device that it thinks is the best device for you automatically, or it allows you to fine-tune, pick a specific device for what you need. And then it'll provide some other functionality for retrieving the name of the function and the queue that you're running on. So the way we implement this is, so we provide an additional overload for the algorithms, like for each year, that take the input iterators and the function, and then we pass it on to our implementation. And from that point, essentially what we do is, so we take from the execution policy, we take the queue, the SYCL queue that was picked to run on, and then we calculate the number of iterations that we want to execute across. So what we do here, where we're calling this function this getInfo of the max workgroup size. What this does is it queries the OpenCL device for what the maximum number of iterations that you can execute at once on that device. And then we do a a calculation based on that to see what the optimal the range should be that we're executing across. And then the next thing we do is we create this command group. So it looks slightly different here because we're defining the lambda first and then submitting it. So essentially this is the same as what you saw before. So we define this command group, and then inside we create an accessor to get access to the buffer. The buffer wraps the memory of the vectors, the input vectors that we passed in. And then from that point we call parallel for. And then inside the parallel for we retrieve the index from SYCL, and we pass that on to the algorithm. So we call the algorithm the function that the user provided. So now I'm going to give a quick demo of what this looks like running. Just have to switch screens. I have to zoom this in a little bit. Oh, there it is. Okay. Can everyone see that okay?
Yeah, looks good.
Okay. So here, essentially, so we have all of the header files that we include. So there's the standard algorithm and execution policy. We also include the SYCL execution policy as well to provide the additional policies that we provide for SYCL. And we define the size of the data set that we want to work over. So in this example, I'm going to show the sort algorithm. So we have this function here, run sort. It takes any execution policy. Essentially what it does, it initializes a vector with a random number of elements specified by the size, so a random value to each element, and then it runs the sort algorithm with that vector and the execution policy. And essentially the rest of the code is wrapping it with a timer to output the time that it took to execute. And then we do a check to see if it was sorted. And if I jump down to here, so we run this function for 4 different execution policies. So the first one is the standard sequential policy. The second one is the standard parallel policy, and the third one is the standard unsequential. So this will be likely run in vectorized. And finally, we have the SYCL execution policy. So the first 3 are run on the CPU, because they're standard C++ policies, and then the fourth one, will run on SYCL, on the GPU. So if I run this, I'll try that again. Oh, there we go. So this is quite small, so it may be hard to see. So essentially here, the first 3 algorithms are relatively similar times. The fastest one is the unsequential. Now here, notice the SYCL execution policy is actually slightly slower than the other ones. So the reason for that is that one of the common problems with executing on a GPU is that if the overhead of moving data to a GPU and back again is quite high. So if the amount of work that you're executing across isn't enough to outweigh the overhead of moving data, then it's often not worth it. But if we go back here and switch to a higher size of data set, and then run it again. So this time, so it's taking a little longer to run. So this time, there's very similar results from the three standard policies, so 1.8, 1.7, 1.6. So the unsequenced is still faster. However, the SYCL policy is running approximately 4 or 5 times faster than the standard policy on the CPU. So this shows you can get a lot of speed up by running your code on a GPU, especially if it's very highly parallel code. However, you do have to keep in mind that the amount of data that you're the size of the task is very important, because if it's not a large enough task, it can be outweighed by the cost of the data movement. Okay, so that's that. So I'm going to pull the slides back up again. Okay, so if you weren't able to see the results there very well, I've put the results on a slide here. So it shows, so the first example is running at 2 to 16 size, and this was where there was very little or no gain from running on the GPU. Then as the size increases, the amount of speed up rapidly increases. Okay, and I'm going to invite Michael back up to talk about the future direction of the standard.
Thank you, Gordon. This is actually quite amazing. So you're saying, so it's actually almost 5 times faster?
Yeah, we're 4 or 5 times faster for this example.
So just to hang on for a moment there with that one, you notice that this is actually on an Intel's, where the GPU and CPU is actually combined.
Yeah.
Okay? And it's a couple of things to note. I'm not trying to bash different companies here, but if it's on an NVIDIA, and potentially if it's an NVIDIA, you actually have even further data movement, bigger data movement. But the NVIDIA GPU will be more efficient and be able to do things a lot faster. Would that be fair to say then?
Yeah, definitely. Okay. If it's a discrete GPU,
if it's a discrete GPU, so different
higher.
Configurations will have significantly different results. So you might have to need a bigger data load. If it's an AMD GPU, for instance, which we have, but we don't, not on this laptop, for instance, then you would actually, it's an integrated GPU, and the results would also be different, but it would still be faster.
Yeah, so the results would vary quite greatly between running on a discrete GPU and maybe like AMD's APU or the Intel embedded GPU.
Wow. Okay. Thank you. Thank you. Thanks. I'm absolutely amazed at the direction of all this that it's taking, because I'm very excited about where we're going to go with that, because when I see results like this, I really want to make sure that everybody is aware of what directions we can go towards taking advantage that last bit of die surface that is still inaccessible to us to C++. Okay? I never want to get to the point where C++ is just going to become a wrapper language and you have to descend into some vendor-specific language so that you have to access the fastest part of your computer. So in that respect, one of the things that we wanted to do is to get C++ towards that direction. Now, it's not a straight path there, we know. It's going to be a bit of meander and sideways movement. And implicitly, the committee all agrees with us already to some extent. Except that until we set the direction, it was all kind of a silently believed direction, but nobody enunciated it until we actually said, yes, we want to go to this point. So if we didn't say it, we might get there, but we might get there like this. And I don't want it to be like that. I want it to be in a relatively straight line, relatively speaking. But even though it's a relatively straight line, it's not straight. To get there, we do have various hurdles to do. One of which is we have to get executors working. Okay? I'm going to show what executors look like. In fact, there's a talk about executors at the end of this week with Gordon and me. Gordon's going to talk about in deep detail. We've been on calls every other week with a bunch of people who are deeply interested in getting executors working, from NVIDIA, from Google, from NASDAQ, and from CodePlay, leading this discussion. Part of the reason is because we've all implemented those executors. I'll show you what they are. We've implemented it in SYCL. NVIDIA has done it. Google has done it. And so has the NASDAQ people. Once you have executors going, you have to get asynchronous algorithms. And because that enables latency hiding. That is fundamentally what's going to be important for this to work well in the games industry, in the fintech industry, as well as in the future of self-driving cars with machine learning. Okay. Next thing we have to do is create this execution context, which may be an actual context object, or it might be an abstract. But certainly, we've been talking across the board with high-performance community across all the U.S. national labs, like Sandia, Livermore, Argonne. In fact, in supercomputing coming up, we're going to host a BOF on heterogeneous and distributed C++ computing with one of the Argonne National Lab people, Hal Finkel. Okay? So when we took these proposals to try to get a general sense of the directions to the standard committee, because these proposals effectively makes it different that we can't talk about flat memory anymore. Now we have to talk about either separate memory or hierarchical memory. The direction, we realized that this would be a very invasive surgical change to the C++ standard that we all love. But we feel it's unavoidable because we can't let the standard lag behind so far. I really don't want to get out there to 2020, 2023, and C++ is still living in the CPU stage only. Okay. They came back and told us we can't look at inaccessible memory yet at this point because we haven't figured out how to deal with affinity yet. That's reasonable. So as such, we are now retasking our directions towards addressing a way to deal with affinity. Affinities in our community is generally dealt with something called HWLock, which is a function you can call on Unix machine that you can sort of get a configuration of the cache configurations, the memory configurations, and things like that. So we have to deal. So we've been working with Sandia National Labs on this design called context and affinity. And the other thing after that is we have to work on something that allows you, as Gordon mentioned, the heaviest price you pay for that nirvana of 5 times speed up is that memory data movement. Okay, and that's different. And this is actually on a system where the CPU and GPU is actually mostly fused together. Okay, can you imagine how it would be like on a totally discrete system? Now we don't know where the future hides, the future holds for us. Whether it's going to be all distributed systems, or whether it's distributed CPU and GPU combination, or whether it's going to be a combined APU system. That really is trying to pick a winner, and we're not in the business of picking a winner in the industry. We kind of want to serve everybody as much as we can. So we have to have some sort of way of governing this policy. Whether we do it through allocators, which is possible, or we have to do it through some sort of library routine that allows you to move data around, okay, in an efficient manner. But don't forget, it's not just moving data around, it's about synchronization as well, too. And then finally, we are working on this idea of an exception in a concurrent environment so that we can make sure that we can handle that particularly well, okay? This is a quick view about executors. Executors act as an interface between the various parallel constructs we have, and there's so many of them, and so that we don't get an n-by-n explosion with the execution resources that we would have. And there are many of these execution resources. Right now, C++ is only pretty much concerned with this. We have provisions for this, and we have nothing to handle the distributed or heterogeneous right now. And that's the future direction that once executor is there, we can enable those directions. Come to Friday's talk, and we'll tell you all about it. So in summary, we talked about the Parallel STL TS. We talked about the history of it, how it integrates with the parallel algorithm, the C++ standard library. For that, we have a class, I think this Saturday, Sunday, with Chris Tabella, that you can join. That we're going to talk about the C++ STL in depth. But we're going to also add a way for you to do. I think we might have a hands-on. I don't know if we do, but we're planning some way so that you can also play with the Parallel STL as well. Okay. And then we're going to we also show how STL runs on CPU. That's boring to us. It's an important part, but it's the other thing that we're excited about, that we can now try to do it on a GPU. And we also talked a little bit about the future directions toward heterogeneous and distributed ISO. As somebody from Sandia said, their goal is to retire OpenMP and MPI permanently so that we can all do it in standard C++. Thank you very much. Any questions? Come on up, Gordon, Chris, come on up. Yep. So in case you guys want to ask any questions of us about some of this stuff. It's exciting, but it's a lot of work. Yep. Go ahead, please.
Just a quick question.
Yeah. Could you the mic?
So just a quick question, like I saw that in your demo that when you try to call GPU to do the sorting or whatever you want it to do, does it have to hold up a CPU thread or can you like give it a callback function? And
so the question is, when you do this demo, do we hold a CPU thread to keep it going?
Yeah.
So do you mean by the CPU thread, you mean in order to schedule the...
do some sort of
Can you like schedule it, for example, if it takes like an hour, can you not hold up the CPU thread?
So essentially in the SYCL implementation, well, our implementation has a scheduler thread. So when you create a queue for executing work on a GPU, there's a thread behind the scenes that runs, a single thread, scheduler thread that runs, starts work and pulls for work on the GPU. So
like when it finishes the workload, how does it send the signal back to does it send us software interrupt or something like that? Or do you have a callback function that you can provide it? Or
so the question is, how does it send the signal back when it, how does it synchronize, in other words, when the workload's done?
So there's two ways that we synchronize with work. So there's an explicit way. So when the queue has a wait function where you can explicitly block and wait for all work that's on that queue to finish. And the other way is that any buffers that are maintained in memory that's been used on a device in a SYCL execution, when those buffers are destroyed, those will block and wait for the associated work to finish completing. So what will happen is when the scheduler thread handles all of the events synchronization behind the scenes, so then whenever there's a host application synchronization, that will trigger for the scheduler thread to wait.
So I want to add that this stuff is actually out in the hand of the community, being used by. We have an open community edition for you to download, and there's now 4,000 downloads, and we have it now have SYCL implemented on TensorFlow, the machine learning language from Google, so that it now can distribute to non-NVIDIA GPUs. The original TensorFlow was only going to NVIDIA GPUs. So now it's all working very nicely. So it's more than just a proof of concept, and we're usually hired to adapt it to any company's specific GPU or FPGA's configuration. So that's why there's a lot of confidence in the execution of all of this stuff. Okay. There's a couple of thank you very much.
Thank you.
There's a couple of other ones, so go ahead.
Hi, this is really cool technology, by the way. The demo is really awesome, so thanks. I have a question more for the design of the parallel algorithms from a perspective of a third-party algorithm developer.
Yeah.
So pre-C++ 17, I could create my own algorithm, and it would kind of just be a peer inside of the ecosystem of algorithms. But in 17, with these execution policies, the barrier to creating a version that can do parallel or parallel in sequence becomes a lot harder. So has there been any thought given to that in the design process? And a thought that comes to mind, last year, Ben Dean gave a talk where he showed you could re-implement all of the STL algorithms effectively using std accumulate. So is the idea that so my thought is, should there be like a core set of algorithms that provide these underlying mechanisms, and then all the other algorithms are implemented in terms of them? Or how can we provide tools to people to make leveraging this cool technology easier without needing to know the guts of SYCL or OpenCL, etc.
Right. So the question is, it used to be a lot easier to re-implement to algorithms for your own specific needs, and now with Parallel STL, it's actually become, the barrier is actually a little higher. Yeah. Is there a way that we can sort of partition it so that it can be represented in different parts? I don't know if that's been talked about. There are other library experts here that might be able to talk a little more about that direction. And I think that's actually a good advice in terms of towards a library group, so that we can do these kinds of, allow the users to be able to do these kinds of things. I don't know if that's been talked about in the library group, so I have to admit that I don't know the answer to that.
Okay.
Okay. Thank you.
Thank you.
Over here. So hey, how are you doing?
Yes. Is there any kind of development or support for Vulkan to kind of minimize the communication pathway between the GPU and CPU? So when you're feeding large number crunching or data or GPU instruction sets, that you don't have to you don't have to necessarily plug in the pathways. You can do that once and then have the GPU work until it's finished and then return the data to the CPU.
Right. So the question is there a way to minimize the data movement between the CPU and GPU? Did you mention Vulkan?
Yes.
Okay, great. I'll take one part of that question. Sorry, I have a cold. The design is, so this is a runtime design. The runtime actually mediates so that it's intelligent, it doesn't move data back and forth unnecessarily. It keeps the data on the GPU until it's absolutely needed. So if you need to go back to the CPU to get some data, it will only do that and not have to copy everything back and forth. Yeah. Okay. The second part about Vulkan, do you want to take that or?
So what was the question specifically regarding Vulkan?
So basically the question was, can it use the Vulkan
APIs?
APIs and libraries to kind of minimize the instruction set.
So I think the answer is right now it's not implemented in terms of Vulkan. It's implemented using OpenCL and SPIR-V.
Yep.
But it could be implemented in terms of Vulkan, and indeed that's a direction that's been asked of us a number of times because it does give you much more efficient path capabilities. And since we're in the Kronos group, and I was just at the Kronos meeting last week in Chicago, we've been talking a lot about that. Okay.
So SYCL at the moment is based on top of it's designed to be based on top of OpenCL.
But nothing says it can't generate, PTX, NVIDIA, or Vulkan directly.
There's no reason it can't be implemented on top of it.
Because it's really an upper layer, right?
In fact, one of the open source implementations was originally based on top of OpenMP.
Right,
so
right. The open source SYCL implementation, we have the commercial one as well as the free download one. The open source one is called Tricycle, and it is based on OpenMP. Okay. Underneath. Okay. Sorry. Thank you. Over here.
So is OpenCL or SYCL as it were, is this a library-based solution or is this a separate compiler?
Okay. The question is this a library solution or a separate compiler? It appears as library and code, but it's actually done using the compiler front end, using Clang. So this is normal in C++. A lot of library section is actually compiler generated. Most of exception is in the library part, but it's actually a compiler. So in this particular case, you see that it's a library call, but it's actually a compiler that's transforming all of that stuff. So it's much more efficient. Do you want to add in?
Yeah, I'd add to that. So I didn't really go into much detail about how the actual runtime and compiler system work in SYCL. Essentially, it's a single source solution. So you write your code once, and it's compiled by two compilers. So it's compiled by the host compiler and the device compiler. The device compiler generates some form of binary representation. We use SPIR. It could also be something like PTX. And then that's compiled and run by OpenCL.
So presumably that's why you have no limitations on using lambdas in these functions, because you can compile it for both the target device and for the CPU?
Yeah.
That's exactly
so there's some limitations on what you can do in the function based on the limitations of OpenCL hardware. For example, you can't do recursion or you can't throw exceptions and things like that, but in general, there's the majority of what you do.
But that's only because OpenCL has imposed those things. But in other formats, other backends, you wouldn't need to have that kind of problems.
Yeah. So cool. if you're interested, we did another talk at CppCon last year where we go much more into detail about SYCL and how the compiler works. So if you're interested, you could check that out.
Thank you.
So just as a reminder, SYCL is a language that's under evolution just like anything else in C++. It's just that it's under evolution in Kronos, that's all. One more. Excuse me.
Hi. When I was deciding about using either CUDA or OpenCL, I saw that NVIDIA is supporting CUDA and most of the functionalities are unavailable in OpenCL. So with this effort, do you think like these capabilities will also come to the C++ standard, or is NVIDIA is willing to support? I believe they were not supporting OpenCL that much.
Okay, so the question, so I understand the question. Given that CUDA is mostly tied to NVIDIA efforts, and some of it is implemented using OpenCL, your question is this going towards the standard? Yeah, because this will become standard, but OpenCL was also standard, but they were not supported. So the answer is that's definitely the directions. SYCL is one of the framework that we want to use as a guiding experience to be implemented into the future ISO C++. Yes. But we're not ignoring other ones like HPX. The national labs have 2 other ones called CoCos and Rajas. There's a couple of other frameworks like UPC++ and things like that. They're all very C++ specific frameworks, just like this. Then that's what we like about them. That's why we're not looking at things like OpenMP, because OpenMP is very diluted in the C++ side. Okay. OpenCL, while it's nice and heterogeneous, is really focused on the C, under C's part. CUDA, is enriching constantly, and it's rapidly moving from C to C++ full support in the last CUDA 8, 9, and things like that. But it's really used as a NVIDIA way of driving the directions of the hardware. It's a way for them to implement, to expose their hardware capability. So we get a lot of learnings from them as well too, for sure. But we can't sort of rely on it as being anything that we can modify or control for the C++ needs. Whereas with something like this, SYCL or HPX or CoCos, we are willing to modify it based on what C++ needs us to modify it, so that we can demonstrate a reference implementation of what for instance, next thing we're going to have to do is, if we do this affinity thing, the context thing, we would have to modify SYCL to demonstrate how this would work in a modern C++ environment. And that feedback loop is extremely important. As you can see from the demonstration with the Parallel STL, that feedback loop is extremely important to demonstrate, does this feature actually work in practice? You know, when we get the exception handling design done for the concurrency TS, which I'm going to propose in the next meeting, we'll have to implement it in something. We can't do it in CUDA, we can't do it in OpenMP because we don't control that. We could do it in SYCL, we could do it, the HPX guys will do it almost immediately. You know, the CoCos guys will do it at national. This is really the most important part of this feedback loop.
Yes.
Hope that answers your question.
Yep.
Thank you. One more here.
Hi.
Thank you. This is amazing. A lot of good questions.
My question is regarding the demo. So in the last one, in the last case where you used the SYCL execution policy, does the entire sort or the workload get run on the GPU?
Good question. Does the workload move onto the GPU when you do a SYCL policy? This is my colleague's answer then.
So in the demo that I showed, so yes, the entire contents of the vector is moved over to, all the vectors are moved over to the GPU, and then the entire sort algorithm is executed on the GPU, and then the results are synchronized back in. So everything's on the GPU, everything's moved there, and then...
So a follow-up question on that is, as I understand that there is a sweet spot between how much you can leverage the computation of the CPU and how much you can do the same for the GPU. And it's important to use both these resources at the same time instead of offloading the entire workload to the GPU. That way we get best of both the worlds. And so is it possible? Is it in one of the is it a future goals that you know, when you give me an array to sort and I sort part of it on the CPU, so I keep the CPU busy, a part of it on the GPU.
So this is a great question. The question is, can we divide up the work between the CPU and GPU?
Yes. So one of the resources are not idle, but they're all working.
Yeah. So actually, Gordon actually teased an answer to that already in the slides.
Yes. So one of the things I touched on briefly was as well as the SYCL policy, we also have the SYCL Heterogeneous policy. So the way that works is, rather than having a single SYCL queue, you have 2 SYCL queues and then a ratio of how you want to distribute the work. So you can say something. You can say I want to distribute the work across the CPU and a GPU, and providing the OpenCL implementation allows those devices to be used concurrently, then that will execute concurrently and run it at the same time. I wasn't doing that for the sort algorithm because the sort algorithm is not an ideal algorithm for sharing across CPU and GPU, because generally you have to. You have to kind of do a lot of work on the CPU afterwards to further the...
So my point is, so this is still not abstracted. It is still up to the developer who's using the SYCL library to decide what goes to the CPU and what goes to the GPU.
Yeah, exactly. Yeah. So SYCL doesn't make decisions about how to distribute the work between devices, but it does make it very, very easy to do work on multiple devices at the same time. And the ability of having the accessors for describing where you want to access data and when removes a lot of the complicated event handling and synchronization that you have in OpenCL. So you essentially say if you want to do work in one place and then in another, or at the same time, you just describe, you say I want to access this memory here, and the runtime handles all the synchronization for you.
Thank you.
Thank you very much.
Thank you. Once again, if you want to try downloading SYCL to the experiment, it's free to download. And like I said, we've had it available since November last year. CoPlay had it, and there's now 4,000 downloads, and it's being used largely by. So there is real experience both from the open source, and we also use it in our proprietary implementations that people hire us to do for the various GPUs and whatever. So anyway, thank you very much for coming, and enjoy the break. Okay, thanks. And come to the executor talk and the C++ library class over the weekend. Thanks. Bye.
Thanks.